This is Stefan Gvozdenovic presenting final presentation in AWS IoT with Raspberry Pi implementation. This project aims to present a cheap, maker-oriented alternative to implementing Lightning control. It involves 4 different pieces of hardware: AWS IoT button, Raspberry Pi version 2, third-party wireless radio, and MyLight light bulb. There are 3 different communication technologies involved. IoT button talks to the Raspberry Pi through AWS via Wi-Fi and public internet. Next, Raspberry Pi talks to the radio through Serial Peripheral Interface or SPI. And finally, radio talks to the light bulb, uses proprietary 2.4 GHz wireless protocol. The most challenging part of the project is the feasibility of controlling the commercial light bulb with the third-party wireless radio. The reason for choosing MyLight light bulb is because it has been proven to work with third-party radios. This project requires MyLight light bulb and MyLight controller. Controller is only used once to link a MyLight light bulb to a controller ID. Since no encryption is used for the communication, it makes it easy for anybody to reverse engineer the light bulb commands by sniffing the radio signals, therefore finding the controller ID necessary to control the light bulb with the third-party radio. This slide shows a system-level overview of the project. Single button click turns the light on, double click turns the light off. IoT button communicates through MQTT protocol to the AWS IoT. These events trigger Lambda function, which is written in JavaScript, which then opens a web page hosted on Raspberry Pi and programmatically presses buttons to switch the light bulb on or off. Website hosted on Raspberry Pi then sends serial commands to the radio, which transmits actually several commands to make sure switching is reliable. This redundancy is because the light bulb does not acknowledge received packets, so we have to send several commands to make sure the switching is reliable. Raspberry Pi interfaces radio through Serial Peripheral Interface or SPI. These are the SPI signals. GND is ground, negative power supply. VCC is a positive power supply. In this case, 3.3 volts logic is used. Chip select is used in cases where there are several SPI devices on the same bus, so the master, in this case Raspberry Pi, has to be able to select which device it wants to talk to. System clock is a signal that is clocked whenever there is data on the bus. Master out, slave in is a data line used by master to talk to the slave or slaves, and master in, slave out is the opposite. It's a data line for slave to talk to the master. SPI is vendor specific, low level protocol. Usually around 2 megabits per second throughput. As I said, Raspberry Pi in this case would be a master and the radio would be a slave. NRF24 radio talks to the MyLight light bulb through proprietary 2.4 wireless protocol. Packet structure can easily be deduced if one presses different buttons on the MyLight controller and captures corresponding packets. MyLight controller is shown on this slide, as well as a packet example with different fields colored uniquely. Thanks to Henrik plots, these fields are reverse engineered. The fields that are of most interest to this project are control fields. Those are color slider field, brightness slider field, and button status field, which turns the light bulbs on and off. Button status field is the only field utilized in this project. Having this project in place, it would be trivial for future work to implement color or brightness control. 4 software layers are necessary for this project, excluding AWS and Lambda function. RF24 repository is a GitHub repository, which is a SPI library for NRF24 radio. It has more capability than is being utilized for this project, since it supports Arduino as well. Raspberry repository made by MySensors open source community is acting as a SPI to serial bridge. Open MyLight Raspberry Pi repository is a MyLight specific program with command messages. This source code is a result of reverse engineering the MyLight light bulb. The last one, Pi Magazine, is a repository made by Simon Monk, which brings all the code together in a simple web interface, which allows us to control the light bulbs. Let us compare a commercial lightning control device and our custom solution. Philips Hue Bridge is a well-known candidate. Philips Bridge runs Zigbee stack, which is a standard, more about it, while MyLight runs a non-standard 2.4 wireless protocol. The good thing about Zigbee is that it uses encryption, while MyLight doesn't use encryption. Another thing with Zigbee is that it can form mesh networking topology, which practically extends the range of the Philips bridge to be unlimited. However, range of the point-to-point network of a Philips bridge is only 30 meters, while estimated range for NRF24 radio, including LNA and PA, is around 800 meters line of sight. The price comparison assumes that the light bulb made by Philips and MyLight are approximately same price, and that this audience already has Raspberry Pi or similar general purpose computer. Disadvantage of Philips Bridge is that it is closed source, while parts of this custom solution are open source and open hardware, which is the Raspberry Pi. MyLight is unfortunately closed source and proprietary. point of this slide is to illustrate different networking topologies of Zigbee. Phillips Bridge, as we already mentioned, uses Zigbee to communicate to Hue light bulbs. Peer-to-peer network is possible, star network, mesh network, as well as a cluster tree, which is not shown in this picture. In purple, PAN coordinators are marked. A coordinator in our project would have been Raspberry Pi. Routers are always active and they route information from other nodes in case of mesh network. A light bulb would be an example of a router. End devices are usually said to be sleepy, which means that they spend most of their time in low power mode, conserving energy and being able to have a long battery life. Note that it does not make sense for light bulbs to be end devices since they have already power from the main power supply. They can be routers, they can always be on, and they can route information and be useful to the network. Good example of an end device would be a battery powered sensor or any other device which has a constrained power source. It is important to make a distinction between Zigbee and MQTT. Zigbee connects router, which is in our case a light bulb, to a gateway, in our case Raspberry Pi. Zigbee also connects light bulbs to light bulbs. Zigbee is a 802.15.4 standard which covers physical and MAC layer, which is first and a second OSI layer. It is a wireless radio protocol and its range is between 10 to 100 meters line of sight, but it very much varies based on the material that the walls in the house are built and such. The throughput is 250 kilobits per second. It is intended for low power, low data rate wireless sensor networks. MQTT is a higher level protocol. It runs on TCP/IP, which means MQTT is higher than fourth layer in OSI model. It connects gateways and server backends. In our case, that would be Raspberry Pi and AWS. MQTT is intended for varying latency and unreliable connections, mainly wireless sensor networks. Since this project has a very brief involvement of AWS IoT API, this is the list of additional use cases. Two-way control can be implemented where light's state can be sent back to the AWS. Motion sensors can be integrated. And generally speaking, light can be triggered based on any programmatic event using a Lambda function. The next slide will show a demo of the project.